Now this part of the MOEM, the mechanics of engineering materials, okay, the mechanics of engineering materials, we'll be looking at elastic constants and the volumetric strain Actually, you can, never mind. Actually, you can see the pointer here. It will be recorded, not on the screen. Okay. So now, earlier we have done what is direct strain and what is the elongation and direct strain due to the direct stresses. Now, sometimes or most of the time when you refers to rectangular bar or cylindrical rods, okay, when you have a force or a load acting on the bar or the rod, it actually, other than giving the bar or causing the bar to go under deformation in the line of the force, it also will cause effect to its thickness or width, okay, to its thickness or width or diameter. So if let's say, for example, when you refer to this case here, the force that we have here, all the forces here, they are actually acting in the axial direction or the axial direction along the axis of the bar. Now what we have done earlier was only the length of the bar is being affected. Okay, so what happened is the length of the bar will increase, but at the same time, in actual practice, in the same time, the width and the thickness of the bar also will be affected. Okay, so what happens if you have a tensile force like this? In this case, you have a tensile force, and this tensile force here actually is causing an increase in length, but at the same time, it also causes the width and the thickness to be reduced. Now, when you refer to cylindrical bar or this circular rod, when the tensile force is acting on it, actually the diameter of the bar will also reduce. That means when it goes longer, the bar becomes thinner. Okay, so any changes other than the length, in this case, any changes other than the length, we call the lateral strain. So for example, if when you look at this circular rod or circular bar here, when you have a tensile force acting on it, which is acting along the axis of the bar, this will cause the length to increase. So if you take the length divided by original length, we have what we call direct strain. But then when you look at the diameter, it actually reduced. It actually compressed or reduced, a reduction in diameter. Okay, when you take the reduction in diameter divided by the original diameter of the rod, we have what we call lateral strain, the lateral strain. So when you look at the notes that I've given here, tensile force causes increase in length, causes decrease in diameter or thickness and width at the same time. So when you refer to the second case here, compressive force. Now the compressive force, when you look at the square bar or the rectangular bar here, the compressive force which is acting on the bar or the rod or on the bar, which is acting along the axis of the bar. Now the force is acting along the axis. So any changes in that direction of the force divided by its original dimension, that means the original length in this case, you get what we say direct. Other than that, let's say you look at the width and the thickness, this compressive force will cause the length to decrease, shortening, but the width and the thickness will increase. So if you take the reduction in length over original length, you have direct strain. If you were to take the increase in thickness over original thickness, you will get lateral strain. and as well as the width. Okay, the width, if you take the change in width over original width, you will get lateral strain. Either the thickness, change in thickness over original thickness, change in width over original width, both will give you the same lateral strain. Or if you take changes in diameter, which is actually increase in diameter in this case, because it's compressive, over original diameter, you have what we call lateral strain. So any changes in the direction of the force, I repeat once more, in the direction of the force, any changes divided by its original, you get what is called direct. Other than that is called the lateral strain, or we call them as secondary strain. The one that changes in the direction of the force usually is called the primary strain or the direct strain. Okay, so here you can see the force causes an increase in length. This is the pulling force, which is causing the length to increase, but at the same time a reduction in the diameter. Now in the next case, you can see the force is causing the thing to be shortened, okay, but okay, at the same time the width and the thickness should be increasing. So the rectangular bar or the square bar will be fatter and shorter. So, and the circular rod also the same thing when it is subjected to compressive load. So any deformation here, it is, I have already defined the term here, any deformation in the direction of the force. So you have to see where the force is acting. Any changes in that direction divided by its original is called direct strain, or is called the primary strain, or sometimes it's called the longitudinal strain. So any secondary deformation, that means in other words we can call it as the side effect due to the force, is considered as lateral. In this case, the diameter and the width or the thickness can be considered as lateral strain, or in all these cases here on the board. So direct strain, the changes in dimension in the direction, the changes of dimension in the direction of the force divided by the original dimensions, that means the length or the thickness, it depends on where the force is acting. So you have what we call direct strain. And then, okay, so in this case is the changes in length divided by original length. Here, okay, this is the direct strain. This is the direct strain. So the changes here, the changes in length divided by original length, you will get direct strain. So the changes in length is x, the original length is L. Okay, for lateral, you see on the board, for lateral, okay, so you have changes in thickness over original thickness. Now this is lateral, okay, because the force is acting along the length, not, okay, in the x or the z direction, is acting along the y direction in this case. So any changes here, the width and the thickness, that will give you the lateral strain. That will give you the lateral strain. Changes in thickness over original thickness, changes in width over original width, the changes in diameter divided by the original diameter. All these cases here will give you a same value of lateral strain or secondary strain. So another term here, which we call the Poisson's ratio. The symbol here should be nu. Okay, nu. Okay, this need to be corrected. So Poisson's ratio is actually defined as lateral strain over direct strain. Usually, and most of the case, not most of the case, the lateral strain should be lesser than the direct strain. So that means the primary strain must always be larger than the secondary strain. The side effect must be smaller than the one that is directly affected by the force. So that will give you a Poisson's ratio, and Poisson's ratio has no unit, it's unitless, and is less than 1. Less than 1. It must be less than 1. Okay? So from this Poisson's ratio symbol we use for Poisson's ratio is nu. So lateral strain from here, lateral strain is equals to direct strain, bring it over, will be multiplying by multiplied with the Poisson's ratio. So and also we know that, okay, direct strain, we know that earlier from the beginning, direct strain also can be equals to direct stress divided by Young's modulus. So you can also write lateral strain as Poisson's ratio times direct stress over Young's modulus. So the volumetric strain. So now let's say we have a rectangular bar here. So the rectangular bar here with the length here y, and this length here the width as x, and this length here as z. The length as the z. Now in this case the thickness as y and the width as x. So now the volume of the rectangular bar, the volume of the rectangular bar is actually x times y times z, right? Volume. Okay, so this is a force which is acting in the x direction. If you were to consider the force Fx acting alone. Okay, so if the force x is acting alone, then you have stress x in the x direction should be Fx, the force that is acting in the x direction. But the area that you consider should be, remember, for direct stress, the area should be 90 degrees or perpendicular to the direction, the line of action of the force. So the line of action of the force Fx here, so any plane that is perpendicular to Fx, that is the cross-sectional area. So in this case is y, this length here y, multiplied by this length here, the z. Okay? So if, let's say, you consider force Fy alone, the force Fy alone without the Fx, then you will have stress in the y direction is equals to the force y, that is here, okay, divided by its cross-sectional area, xy. So xy you have here is, this is the x, and this is the y. So this is a cross-sectional area, 90 degrees or perpendicular to Fy. Now, if we consider Z alone, the force of Z alone, then you will have this. And then the area will be the X length multiplied by the Z length. So remember, the area is being perpendicular to the force Fz. So, and we know that original volume is actually the X length times the Y length multiplied by the Z length here. Okay, so that gives you the volume. Okay, so that will give you the original volume. Okay, that will give you the original volume of X, Y, and Z. Okay, so applying partial differentiation, we are using partial differentiation here to determine the changes in volume. Why we are using partial differentiation? Because here the volume is a function of not only one variable. the function of, here you can see, is x, y, and z. So that is why we cannot use the normal differentiation method. So we have to use what we call the partial differentiation. So partial differentiation basically says that when you take volume changes with respect to x, that means you are assuming that the volume only change because of the x length changes, but not the y and the z length at that moment. And then if you take the changes in volume with respect to only y, then you consider that the changes in volume only because of the changes in y length, not the x and z. That means you have to keep x and z at that moment as a constant. Then, or if you consider the changes in volume is because of only the changes in z, then the x, y should be kept constant. Okay, so here you have, now you are differentiating, okay, or the partial derivative of v with respect to x. You are working out the partial derivative with v with respect to x. That means you are looking only the changes in volume with respect to the changes in x length only, where the y and z at this moment you must keep it as constant. So when you differentiate that v with respect to x, this becomes 1, and the yz is a constant. So therefore you have this equation here by bringing the delta x onto the right hand side. Then you have the partial derivative of v with respect to y. So you have the delta v is equals to xz delta y. Or when you consider the partial derivative of v with respect to z, then you will have this. Okay? So that is the application of your partial differentiation. So therefore now we work out the total change in volume here. This is missing. This should be delta again also. Okay, this should be corrected later. So the total change in volume. So what you need to do is you just need to add up this with this and this. Yeah. So you have the total change in volume. So if I want to find volumetric strain, remember strain is always defined as changes over original. So when you say volumetric strain, so you will have the change in volume over original volume. So therefore, so you put in your total change in volume, that is written here on top, and then divided by the original volume here, so you get the volumetric strain. Okay, so when you look at this yz, so you cancel off with your yz here. When you refer to this xz, so you cancel off with your x and z here. If you have x and y here, so you cancel off with your x and y here. So you come to this equation here, where your volumetric strain is equals to delta x over x plus delta y over y, and plus delta z over z. Okay, so we know that the changes over original, and the changes over original is actually equals to the strain in that respective direction, x, y, and z. So delta z over z, so you have epsilon z. Delta y over y, you have epsilon y. Delta x over x, you have epsilon x. Okay, so and now the sign convention that we have used since from the beginning is we consider tensile as positive and compressive as negative. So we know that direct strain, and we know that direct strain is equals to stress, direct stress over Young's modulus. And also we know that lateral strain, just now from the earlier slides, okay, is equals to the product of Poisson's ratio to your direct strain. Okay, so we have this earlier from the previous page, right? So this one. Okay, so now before we go to the slide of the next page, now see here, epsilon x. So when you write epsilon x, the equation for epsilon x, that means when you write the equation for the strain in the x direction, the direct strain in the x direction, that means you should be looking at fx alone. If fx is acting alone, that means any direction here, would be direct, the other two will be lateral. The force is here if you consider fx only. So if fx, then any changes in this direction is direct, any changes in this direction and that direction is considered as lateral. So, and also you know that if you were to consider only the force in this direction, that means this line here will goes under elongation, whereas the other two will undergo shortening, compressive. So whenever is tensile is positive, and whenever is compressive will be negative. So when you refer to this case here, for example, that means you have direct in the x direction, lateral in the y direction, and lateral in the z direction. Okay, so when you consider the strain in the x direction, then the direct will be in the x, the lateral will be in the y and the z. But then why there is a negative sign here? Because this is positive, because this is tensile, both of these are compressive. Then when you refer to epsilon y, then the sigma y over E should be direct tensile. Then the new sigma x over E should be compressive, and the new sigma z over E should be compressive. Direct when you refer to y. When it is z, then you see z direct, x and y lateral. Always you can see it is accompanied by two negative signs here because they suffer under compressive. When one side is tensile, the other two sides must be compressive. Okay, so once you have got all these equations here, epsilon, x, y, and z, we substitute into the main equation of volumetric strain. So you have all these things here. Then when you rearrange this whole thing here, okay, you will come to the final formula, that is this. This is your final formula. Okay, so the next slide. So in this next slide, I've given you, okay, 5 different cases. The first cases to find the volumetric strain in the x direction only, because now you have only sigma x. So that means as compared to the previous equation, your y and z are gone. So that means you have neglected the y and z. So you see here, there is no y and z here anymore. So originally this should be sigma x plus sigma y plus sigma z here. But then since there is no x and y and z, so they have been ignored. So it is only sigma x over E. Then the next one you can see is only the y and the x, where the z is not there. So you can ignore or neglect the sigma z. In this case, all the 3 are there. So you will see your sigma x, y, and z are there. And then this case here, okay, if let's say for example, this 3 sigma, this should be a cube actually. This should be a cube, okay? This is one more mistake that I have made. If these 3 things here, the y, sigma x, and sigma z, if they are of the same magnitude, then you will have sigma x, which is equal to sigma y, which is equal to sigma z. When you add it up, it becomes 3 sigma divided by E. And if let's say, for example, you have a cube that is submerged into water or seawater or anything else, then it will be subject to compressive from all directions. Then this 3p or this 3 sigma will become negative 3p, where p is the pressure. Remember, pressure for fluid, sigma, that is a stress, is for solid. Okay, and the next part is the elastic or the material constant. Okay, we call it as the material constants or the elastic constants. This should be Poisson's ratio nu, and this is the Poisson's ratio nu here as well. So this part here, it only shows you, okay, we need to derive, if it is required, to derive out this equation here and this equation here if it is required. So on the later slide. Okay, so this will give you the relationship between this formula you can use to determine either the G, the E, or the Poisson's ratio. It depends on the question. which of this is to be determined. So you can use this formula or this equation here in order to find out G actually, because it is equals to the Young's modulus divided by 1 plus Poisson's ratio. Actually, you should have a 2 out here in front of the bracket. It's another mistake made by me, sorry. Or when you refer to this relationship here, then you can find out the K, which is called the bulk modulus, and you have the Young's modulus divided by the 3 in front here is missing again. 1 minus 2 times Poisson's ratio. Okay, 1 minus 3 times 1 minus 2 times Poisson's ratio. Am I right? Okay, here you have this G here we call shear modulus, Young's modulus, Poisson's ratio. Outside here you should have a 2. Okay, sorry, that is why I have put it into your podcast, your MP4. Okay, that's all for today. Thank you. If you like the video, please subscribe and like. Okay, so this is your tutorial. Okay, so you can work out your tutorials, but then the solution will be given later on. Okay, thank you very much. Bye bye.